Okay, this video is going to show you how to use what's called the Molar heats of formation method. We're going to use this to figure out net energy. Net energy is delta H. We're also going to use this to figure out molar heats of reaction, which is capital H. Okay, so the questions will look like this. It'll say, using the molar heats of formation method, calculate the net energy. So this is the thing we're looking for, one of them. Change for the reaction written, and calculate the molar heat of reaction of the substance underlined. So again, we're looking for a delta H for the reaction and an H for the reaction. Okay, so the first thing that we're going to do is it kind of has a whole bunch of steps, very similar to the heating or cooling curve, but we have to do steps. So the first step is to write out a balanced reaction. So this is going to show how good you are at this and how much practice you need. Okay, you shouldn't have to look up what methane is, right? Because we should know what it is from doing organic. But methane is CH4 and it is a gas. If methane is burned, because here's what I'm writing out the reaction for. If methane is burned, that means I have to have oxygen. Oxygen is a gas. What I always make when I burn a hydrocarbon is I make carbon dioxide and I make water vapor. Okay, to balance this out, I'm going to have a 2 in front of the water. That makes 4 hydrogens. And I'm going to have a 2 in front of here to make 4 oxygens so that there's balanced. Okay, step number 2 is that we're going to find the heat of formation of everything in the reaction. Okay, so we're going to use our data booklet for this, and what you'll see is that on page 4 and 5 there's a molar heats of formation table, and everything's in alphabetical order. So you'll see that actually if I turn to page 5 in the data booklet, we'll see methane is actually there, and it says to form methane, and I'm going to write it right underneath methane. I have 1 mole of it, right? The reason I know I have 1 is because there's nothing written here that tells me I have 1 mole of it. Okay, 1 mole of methane is 74.6 kilojoules per each mole. What that number is it tells me exactly how much energy it takes to make methane. So what I'm doing is I'm taking 1 carbon and 4 hydrogens and adding them together, and this is actually how much energy is actually given off when I make methane. So this is an exothermic reaction, right? Because you can see that that's negative there. Okay, then I want you to look for oxygen. What you should see is that oxygen is actually not on the list. You actually won't find any element on the list. There's a really important reason for that. There is actually no elements on the heats of formation table because elements are naturally occurring in nature. It doesn't take any energy to make them. They should already be made. There shouldn't be any heat of formation, so you won't see them anywhere on the table. There's not a single element. All the things that are listed there are all compounds. Okay, and next we're going to look for carbon dioxide. So carbon dioxide, again, there's only 1 mole of it. And carbon dioxide is negative 393.5 kilojoules per mole. And then I have 2 moles of water. And notice this is water vapor. Unless it says otherwise, like you'll see sometimes it'll say it made liquid water, we always assume that it's actually water vapor and it's actually a gas. You'll actually notice that when you look at the heats of formation table, there's actually 2 numbers for water. One is for the liquid and one is for the vapor. So in this case, we're going to use the vapor, right? So it's 241.8. Not using the right number could make you come up with a different answer than everybody else. So you want to make sure that you have the right answer. Okay, now you'll notice that I wrote the mole in front. We do this so that remember to cross this off afterwards. Because what we're going to do is we're going to take now, we're going to figure out the delta H. So we're going to do this by we're going to figure out net energy. We do this by taking the sum of the products. Notice that sum means I add, right? And we minus it from the sum of the reactants. Okay, so what I'm going to do is I'm actually going to add up I'm going to go 1 times 393.5, and I'm going to add it to 2 times negative 2, and this is negative 2, 241.8. So that would be my sum of my products. I only have one reactant, so it's 76.4.6. Again, moles cancels off moles. Okay, so negative 393.5, and we're going to add it to 2 times negative 241.8. So that gives me a total of negative 877.1 for my products, still minus my 74.6 kilojoules. Okay, notice that when I have two negatives right here, they actually turn into a positive, right? So we're actually adding now 74.6 to our negative 877.1. So we get negative 802.5 kilojoules, and that is my delta H. Okay, people get so excited that they got this far and they think that's the end of the question, but that is not the end of the question, right? All you've done is figure out the net energy. We still need to figure out the heat of reaction, or the molar heat of reaction for methane. Okay, so we're going to keep going. So now there's one more new formula that we have. Make sure that when you do this, it's really clear that I can actually see this, what we have here. So make sure I see that you actually figured out the delta H before you start the next part. Then you start the next part. Show me the formula. What we take is the net energy and we divide it by the number of moles. Okay, so we're going to take the net energy from our question, and we're going to divide it by the number of moles that we had. And the number of moles does not come from a calculation, it actually comes from the balanced equation. So what we're looking at is this number that's in front of whatever it was that was underlined. In this case it was methane. So the 1 is in front of it, so that means that I only have 1 mole of it. Okay, when I divide that, I'm going to get basically the same number, right? But it's going to be in kilojoules per mole now. And what I figured out is the net energy of methane. Okay, I'm going to look for two parts of the answer. If you only get this far, you only get half the question. If you get this far, you get the whole question. So you have to show me that you actually figured out the net energy for methane. Okay, let's try another one. So we'll do it for octane is burned. This is actually number 2 from your second worksheet. So octane is burned. Okay, so again, you shouldn't have to look at anything. You could look at your data booklet, but you shouldn't have to for what octane is, because you should remember how to figure out the formula of octane. Okay, it's burned and it makes carbon dioxide and water vapor. Okay, and then you need to balance it. You'll notice that there's 8 carbons here, so I might want to put an 8 in front of here. There is 18 hydrogens, so I'm going to put a 9 in front of here. Okay, what happens is that I have 16 plus 9 oxygens over here, right? So that gives me 25 oxygens. There's no number I can put in front of here that's going to make 25, so I'm going to show you a trick now where we actually put 25 here and we double everything else. So this becomes 2 because it was 1. This one will become 16, and this will actually become 18, just so that you can see it. Okay, and if you actually look, you'll see that it's balanced now. Okay, and remember that the second step is to figure out the heats of formation for each. So we're going to go 2 moles of methane, and when I look at octane on the data sheet, it's 250.1 negative kilojoules per mole. Again, there's no oxygen because oxygen's an element. We have 16 moles of carbon dioxide, which are each 393.5 kilojoules per mole. and we have 18 moles of water vapor, which is negative 241.8 kilojoules per mole. Okay, then what we're going to do is we are going to figure out the net energy first by doing a total, right? So we're going to do the sum of the products versus the sum of the reactants. So maybe on here we'll do this. So we'll do 393.5 times 16. That gives me negative 6296. This gives me negative 43524. Okay, so adding those two numbers together, that means that my sum of my products is negative 648.4. Notice that moles cancel off moles, moles cancel off moles, so I get kilojoules. Okay, and we're going to minus the sum of the reactants. So that means I'm going to do 2 times 250.1. So that's going to give me 500.2. I'm going to make that neater. Let's try that again. Okay, and again we have two negatives, right? So that actually turns it into a positive. So this is the net energy for the reaction. That actually means it's a very exothermic reaction, right? It's actually giving off lots of energy. The reason I know it's exothermic is because this is negative. Okay, now we're going to go on to H. So I have to figure out the molar heat of reaction of octane. Remember that octane was the thing that's underlined, and it's asking me to figure out the molar heat of reaction for it. So now to do this, we're going to do delta H divided by N. So we're going to take the negative 1014.8 kilojoules, and I'm going to divide by 2 moles. Again, I'm not figuring out this number of moles, right? I get this from looking here at what's in front of here. So I'm going to divide by 2. That means for each mole of octane, it actually gives off this much energy. Make sure that I can clearly see that this is the molar heat of reaction, the capital H. This is the net energy. You actually have an answer for it. It's actually in kilojoules, that this molar heat is in kilojoules per mole. Great, so now you should be able to do worksheets 1 and 2.